Good evening, everyone. Look, thank you very much for coming tonight. Tonight's speaker is Professor Madhu Bhaskaran, who's with the Functional Materials and Microsystems Research Group at RMIT University. Her work has been widely celebrated in numerous awards, such as the 2020 Frederick White Medal by the Australian Academy of Science, the 2018 Apex Science Prize for Innovation, the Research for Research and Education, the 2018 Badham Medal by ANZAAS, and the 2017 Australian Museum Macquarie Medal Eureka Prize for Outstanding Early Career Researcher. She's a migrant to Australia and a passionate advocate for diversity, is on the board of directors for Women in STEM Australia and on the advisory board for STEM Sisters. We are also pleased to acknowledge support by CSL for the ANZAAS Melbourne Science Talk series. Please feel free to type questions in the chat as we go along, but we will be addressing them at the end of the talk so we don't interrupt the flow. So make sure they're clear, and otherwise we'll ask you to elaborate upon your question. So I hand over now to our speaker tonight, and thank you very much. Please begin.
Thank you, Malcolm. You can see that now. All right. Thank you very much for this opportunity to present in this forum. And before I start, I'll commence by acknowledging the traditional custodians of the land and also pay my respects to the elders past, present, and emerging. So that's the title of my talk, but always before we plunge into the future, we have to take a little bit of a step into the history and into the past. So that's the plan today. So go a little bit into the past, talk to you a little bit about the challenges and then what we did, and then how we are actually hoping to translate some of the research which we do within our labs, work with industry partners, and how we're actually translating it out into real life. That's the outline of what I'm going to speak about today. So I'll start off by telling you who am I. Basically, I'm an electronics engineer. So I'm a professor of electronics engineering at RMIT University. I'm almost kind of an electronic materials engineer, if I can put it that way, because what I essentially research is the materials which go into electronics. How do I make them better, more functional, better in performance and things like that? So that is kind of where I come from, electronics, but more of materials come electronics engineering. So I'll delve a little bit into my motivation. So what got me into electronics engineering and also what got me into doing the research I'm doing currently. We'll talk about the electronics which you have with you today. More importantly, how are they made and where are they being made currently? And then the future electronics, where to from here? What are the challenges which we actually faced with? And therefore, the research innovations which kind of tie back to those challenges. And then, like I mentioned, I'll talk about some of the examples where we take the tech out of the lab and into the commercial world in the form of wearables or nearables. That was my motivation. So I grew up in India. I came to Australia back in 2004 to pursue a master's in microelectronics. I'm not that old to see the first telephone, which you see in the screen over there. But when I started using the telephone, it looked more like this. So back in the 80s, you would see telephones which look more like this. But very, very quickly, you saw the evolution in this particular space. It's a communication evolution, but for me, it's also an evolution in electronics. So you can see the miniaturization of electronics as you kept seeing phone after phone becoming far more functional than the previous model was. I remember being tethered to the wall because that's where the phone was stuck, and trying to have a private conversation was quite hard when you're trying to do that. And then the cordless phone felt like a big liberty compared to the phone which was tethered to the wall, because it meant you could walk around your house and have that conversation. And then, of course, mobile phones came into our world. And I don't think we have quite looked back ever since then, because it means we are very connected, whether we want to be or don't want to be, anywhere, everywhere, all the time. And you see that miniaturization keep going in this particular space. You're also seeing more and more functionality being added to this particular space. But that's not just the case with the telephone. It is just one among the many smart devices examples. Take any electronic device around you, be it a laptop or be it a tablet, which again didn't even exist for quite a while, but now I can't imagine a pandemic without the tablets and phones, and allowing us to still stay connected in spite of the fact we are so separated across the world right now. So I'll maybe go into the electronics today. And For most people, I'm not sure, the audience who are there in this in today's presentation, but if you are not already aware, obviously a lot of the electronic devices which we have around us have inside them what are called integrated electronics or integrated chips, ICs as they are otherwise called. Now that looks pretty much like what's shown over here. The workhorse of the entire electronics industry is silicon. So we build our devices on silicon. Silicon has exactly the right characteristics which we need for electronics, and which is why we build our entire electronic device on silicon. But the fascinating thing about silicon is it comes from sand. So what starts off as sand eventually makes its way through a lot of processing steps and through a lot of manufacturing areas, and finally ends up as a chip within our electronic devices. So what I'm going to try and explain to you is a little bit about how sand becomes silicon, becomes electronic device. And then I'm hoping I can play a video which kind of just encapsulates the whole thing. So what starts out as sand? No, sand obviously is silicon dioxide, a lot of other impurities in it. You'd really need purified sand or purified silicon to actually start off to make the semiconductor chip. So it goes through a very high temperature process which essentially purifies the sand, at the same time crystallizes it to give you your silicon ingot. So you go through very high temperatures of 1200 or even beyond degrees centigrade, keep crystallizing it and pulling it out and create this entire bowl of silicon, which is extremely pure, highly crystalline. And it's a silicon bowl which is sitting over there waiting to be diced up and used for your integrated chips. So these are the bowls of silicon. Now you can make them in different diameter sizes based on the equipment which you have and based on the end application. But then what you end up doing is dicing it precisely and creating your silicon wafers. So silicon wafers are pretty much where the entire process starts at. And then you undergo multiple processes. So the silicon, as I said, is just the substrate or the base for the entire electronic chip, but it also has semiconducting properties, which means it's neither an insulator, which does not conduct electricity, or a conductor, which conducts electricity. It's in between the two. So it's a semiconductor, which allows you to turn off and turn on, and therefore you get your switch characteristics, which you need for your electronics. You don't want your electronics running all the time. You don't want to be off all the time. You want to be able to control the current flow in it, which is what silicon allows you to do. Now on this, you do a lot of processing, like I mentioned before. And the fascinating thing about this is you use light quite often in this processing. So to make your multiple devices on your silicon wafer, you use a lot of light in the entire process. It's very similar to the way photography was done, say, back in the 70s or the 80s. So you took a photo and then you had to develop it for you to actually get an actual copy of it. It's a very similar process, just scaled down to very tiny sizes. So just to explain scales in this, we talk a lot about microns or about nanometers. Now, a micrometer is 1,000th of a millimeter, and a nanometer is 1,000th of a micrometer. So you're talking extremely tiny scales, but only that allows us to pack in so many electronics and still keep miniaturizing it and still keep things functional. So what happens is multiple steps of these light-based fabrication, which happens. You keep building layer on layer on layer. So it's not just the silicon. If you look at the silicon chip, I'll show you a cross-section of a device shortly. You'll see there are multiple layers in it. Now, each layer has a particular end application. Some of them are metals, which is just conducting pathways. Some of them are oxides. They have a specific role to play in that particular device. Some of them might be dielectric materials, or you might have other materials over there. So each one has to be patterned using very similar processes, and you're just building stacks of it on top of the silicon. So a processed silicon chip looks pretty much like the image on the left. The colors you see are because of the layers having different image contrast, and therefore you see a very colorful looking chip. Zoom in a little closer into it, you'll start to see some of those patterns or features I was talking about with the naked eye. But that's pretty much the size of some of the chips that you're looking at. That's a rice grain, by the way. So tiny, but it's packed, jam-packed with materials, jam-packed with a lot of layers, and jam-packed with functionality. So if you cut that up and look at it at the very nano scale, you would see it looks pretty much like this. Very complicated, interconnected network of many materials, each of which have a role to play. Looking at a cross-section on the right over here, you can see the silicon is actually at the bottom of this whole thing. And this is just a blown-up image to kind of actually allow you to appreciate the number of layers over here. And this is the same thing, which is just repeated and built one on top of the other. So you can see you can have up to 8 intermediate layers sometimes and up to 5 global layers on top. And you just keep building on this to get the functionality which we need to get in our devices today. What I'm going to hope to do is play this video now, and hopefully that encapsulates kind of what I've spoken about so far and just helps you understand the entire process of how a chip is actually made. So this is from Intel, and this is one of the, I think, reasonably latest technologies. They keep miniaturizing further and further. So hopefully this gives you a good understanding of, the thing. I hope that video kind of encapsulated, what I was trying to convey through all those images. But that's pretty much the entire process, repeated multiple times to make your electronic chips. So I spoke about how tiny some of those devices are. I spoke about, micro-sized devices, nano-sized devices, really, really tiny devices. So when you make these devices, where are they being made? And some of the areas which they're being made look pretty much like this. So they're called clean rooms, and quite simply because they're really, really clean. And we use HEPA filters, which are very similar to, the filters which you have in your vacuum cleaners, and you filter out the air in that entire space. So it's extremely filtered air, which does not have any contaminants floating around. Clearly, the size and the scale at which we are working means every contaminant is going to damage devices or destroy multiple devices. So we just cannot afford to have any kind of device, any kind of contaminants in the air or around the equipment where we're making these devices. Sorry. Now, the image on the left is from one of the clean room processing facilities where you see people gowned up from head to toe. We call these bunny suits. It's quite unlike most labs, because into a typical lab, when you go in and you wear your lab coat, it's usually a chemistry lab. And the reason you wear a lab coat is because you're protecting yourself from the chemicals in the lab. This is quite the opposite. So where you're wearing a bunny suit because you are the contaminant and you're protecting the lab from yourself. So it's kind of almost like a flip thing, because it's no longer about protecting sometimes you do have to, it's kind of, it does serve a dual purpose, because sometimes you may be using dangerous chemicals, and so you protect yourself from the lab as well as, protect the lab from yourself. But more often than not, this level of, protection which you wear is because you don't want to be shedding your skin, you don't want to be shedding, your eyelashes and things like that, and destroying the hundreds or millions of devices you're trying to fabricate that particular day. Now, the image on the left is from one of the many clean room facilities around the world where chips are made. The image on the right is from, you can see me in the middle, if you can identify me in that bunny suit. But that's a clean room facility which we have at RMIT. So we have a micro nano research facility at RMIT. It's one of those fabulous facilities where we get in to go wear these bunny suits and make our research dreams come true. So again, some more images of the micro nano research facility, and pretty cool image of me on the right over here, carrying one of those devices. But that's pretty much how I got, enticed into doing a PhD in this particular field. I came here to do a master's in microelectronics, and I was going to do my master's and go back to India until I did a project. And I did a project inside one of these labs, which allowed me to gown up from head to toe, think of an idea, and then go and implement it and make my own silicon chips and test them. And I was hooked. The idea of that I could go do this, make my own silicon devices and make my own electronic chips. That's what enticed me to, staying on to doing a PhD and then stay on to continue a career in this particular path. If you've not been inside RMIT, or you've not seen one of these labs, it's highly possible, because it's actually a very hidden facility in some ways, not intentional, but that's just the way it worked out. So it's one of the old heritage listed buildings, and we have the micro nano research facility kind of hidden away in a heritage listed building. Obviously, when things return to normal and you're looking for a tour of the facility, get in touch with me. I'm happy to take people through and give them a tour of the facility as well. So I spoke a lot about the electronics as they stand today and how they are made, and in nice places such as Intel. I'm kind of steering away a little more away from the typical IC or the electron or the integrated chips, and I'm going to start talking a little more about wearables. Now, wearables are a little more a different kettle of fish. It need not necessarily involve the complicated integrated circuit technology which Intel needs. Sometimes you might not even need too much silicon in a wearable device, because you're just looking at to do one particular purpose. Invariably, it's a sensor which is picking up some kind of a thing around you. But if you look at the term wearable, you kind of tend to think that it's a market which has just caught on in very recent years. But then if you truly look at the history of wearables, you'll see that in some shape or form, we've had wearables for quite a long time. It's just the definition of the word wearable, I guess. So you can go back all the way to the calculator watches back in 1975, or your digital hearing aid is also wearable technology in a particular, if you think about it in the real sense of the word. One thing which ties all of these together is they're all wearables. They are undergoing the usual miniaturization and they're shrinking down in size. But to me, they are still clunky. They are still a little clunky. They're not truly wearable. True, you wear them on yourself, but they're still a bit rigid. They're still a bit hard, and they're still a tad clunky, and they're definitely breakable. Many of you might have this experience. You might have seen your smart devices look like this as a result of just a small fall or something like that. And the problem with smart devices is obviously they are made with a lot of rigid and hard components, which are not really used to wear and very rough handling. So any kind of it falls by mistake, the screen cracks. The screen is obviously made of glass. There are a lot of brittle components inside there which break from time to time, and one can never quite fix them all by yourself. So there's a lot of things happening in there which doesn't allow us to go in and engineer and fix the problems in the smart devices, which might happen as a result of them falling down. So what do we really want our smart devices to look like? If you ask me, this is what I envisaged. Imagine having devices in the future which are very thin, which are bendable, which are unbreakable, and you can literally roll it up like a little rubber band and put it inside your pocket. You never really have to worry about it falling down and breaking ever again. You never really have to worry about the rigid components in there and how susceptible they might be to breakage, or you don't have to worry about those kind of things. That's probably a kind of a future which I envisaged when I started working on this particular piece of technology in 2011 or 2012. So it's been a technology we're working on for nearly 10 years now. And I'll talk to you a little bit about the challenges we encountered and how we managed to overcome some of those. So if you go back to your smart devices or your wearables, these are some of the things which we now envisaging, right? So we're talking about having sensors being placed on your body and or on your clothes or just around you, which are able to do different things for you. It might either be sensing the world around you, or it might be sensing you, the things within you. So maybe you're trying to get a better understanding of your own health by understanding your skin temperature or your ECG or your pulse rate or your blood oxygen levels. Or maybe you're trying to understand the world around you a little better. What's the amount of UV which is present around you? So how much sunscreen do you actually need to protect yourself on that particular day? Or is there a dangerous gas around you which you need to be aware of, and therefore you need to protect yourself or just walk away from that entire place? So things like this are what we envisage will be in the market in the next, a decade or so. And that just helps you understand and make better choices for things which are around you or within you. Now, how do we actually make something like this? And again, what do we want these to be? We ideally want these to be what we call a stretchable, or sometimes it's okay even if they are flexible. Now, these are two terms which are used very interchangeably, but they actually mean very, very different things. A stretchable thing is something which stretches. It's a bit like a rubber band. You can stretch and it goes back to its original state every time you keep pulling it apart and then bringing it back to its original position. Skin is actually in some way stretchable. Flexible is something where it is bendable. It's more of it's bending because it's extremely thin. So flexible is not exactly the same as stretchable. Or something which you consider stretchy can withstand a lot more strain than something which you consider flexible. But you don't always need things to be stretchable or flexible. It just depends on the end application. So for something like that, you don't need the substrate to be silicon anymore. It needs to be something like a polymeric material. So like a plastic, which is extremely thin and therefore is flexible, or a rubber, like a contact lens type material, which is very stretchable and very skin-like in its appearance. We need conductive layers on top of this. So metals which actually form the electrical connections. So these metals, again, need to be stretchable or flexible, or need to be able to withstand that multiple cycles of strain for you to actually make your smart devices for the future. And obviously you need a functional layer. So something which is actually going to, pick up those changes, external changes which are happening around you, or your internal changes which are happening within you. And generally those functional layers, one of the popular choices are what are called metal oxides. So an oxide of any metal which is around you, which is known to you. And the beauty about metal oxides is they're very versatile. So when you change the metal oxide, you essentially change the particular sensing performance that you get out of it. And that's what lends to the functionality of the sensor. So step one was obviously overcoming a challenge around stretching the metals. Now it's kind of intuitive. So if you look at all these, they kind of look similar to a spring-like structure. So the idea behind this was you can no longer have metal connections which are just straight lines, because if you have a straight line of metal and you end up applying strain on it or stretching it, you end up getting cracks in the metal. And once you get cracks in the metal, they're no longer good enough to be used as an electrical connection. They no longer actually conduct the electricity continuously from end to end. And so you can no longer use them as in the circuit. So you needed to have a way by which you can have metals in the circuit. You can strain them and apply stress on them, and they're still being able to continue to keep working as a conductive element in the particular circuit. One way to do this, which a lot of researchers kind of landed up pretty much at the same time, is if we can structure them as a serpentine or structure them a bit similar to a spring, then hopefully we can keep applying multiple cycles of strain and still keep retaining their conductive properties. So if you look at a lot of the wearables around you and you see metals incorporated in them, you will see the metals actually take this kind of a shape. They're not straight lines anymore. They are serpentine in nature, just to allow for that extra amount of strain. That's the metals aspect of it covered. But then how do you make something like oxides? The metal oxides actually stretchable. This was a challenge which I think was much more than, it was much more harder to overcome than the challenge which we had with metals. And that predominantly is because of the fact that they're fundamentally very, very different to the substrate on which you're trying to use them. So you have a polymeric or a plastic material sitting as a substrate for your sensor, and then you're trying to incorporate a functional layer, which is the oxide on top of it. Bear in mind, these are extremely different materials. They're as diverse as you can get in terms of diversity. You have your metal oxides. The reason I use the stained glass image over here is because the colors in this stained glass are actually being lent by the different metal oxides. So as diverse as you get the metal oxides and the colors over there, that's as diverse you get in properties. But generally, oxides are like glass. And if you can imagine them to be glass in the form of thin layers or thin films, it's basically extremely brittle. So you have very brittle oxide layers, which are trying to combine on a very flexible and a very stretchable polymeric base. The thermal stability of the two are very, very different. Now you can, crank up the temperature on an oxide layer up to, 600 or 1000 degrees centigrade, and they'll still be okay sometimes. Try heating up a polymer layer to anything beyond 120 degrees centigrade, you'll just have a gooey mess in your hands at the end of it. So thermal stability wise, they're very, very different materials. And that again lends to the difference in the processing conditions. Generally, oxides, you need to use very high temperatures to actually manufacture them so you can actually get them working the way you want them to work. Whereas you can't really subject your polymers to those kind of high temperatures. So that was basically the kind of challenges which we had. And we were wondering, how can we actually manage to make these oxides, somehow get them onto a polymeric or contact lens type material and get them working with each other. The slide makes it look like it's very simple, but it took around 2 or 3 years worth of work for us to figure out that there is a way in which we can actually grow the entire oxide, develop our entire circuit on a silicon or on a rigid substrate, and then find ways to cleverly transfer it over from a silicon substrate onto your polymeric layer. So what we ended up with as a result of that is what you see pretty much over here. I'm not sure how visible it is, but again, I'm holding one of these in my hand. So that's a polymeric material, a bit like a contact lens type material. And you can see what you has in it is layers of metal. It also has a layer of the oxide layer in there. And as you can see, I'm stretching it, I'm flexing it, I'm bending it, and nothing really happens to it. It still retains its functionality.
Nice things.
You did it for me. You're a bloody genius.
Could someone mute their microphone, please?
So we were amazed that we managed to do this, and we were trying to understand how do we manage to do this. And so we looked at the oxide layers under a scanning electron microscope. So this is an extremely high magnification microscope. And when we saw the oxide layers at the high magnification, we realized it's no longer a thin film. It's no longer just a beautiful thin coating of oxide layer, which is just sitting there. It's kind of taken the shape of overlapping plates. We really liked this. We thought it looked a bit similar to the geological plates which make up our Earth's crust, so we call it the microtectonic effect. And what you have over here are basically overlapping plates of oxides. So what happens in this particular case is when you stretch it, as long as the oxide plates are maintaining electric contact with each other, they are still functional. But if you stretch it too much and they lose contact with each other, then they're no longer very functional. But the minute you slide it back, they again go back and they slide on top of each other again, and they go back to the original state. So what this means is it allows you to strain this up to a percentage of around 18 or 20% of strain and still keep getting it as to be functional as it was at 0% of strain. Now, 18 or 20% of strain is quite an important number because that's how stretchable our skin is. So any kind of wearable application where you're imagining sensors sitting on our skin, you want it to be able to withstand around 18 to 20% of strain. And then, you're good enough to go in terms of it sitting on top of your skin and still continuing to keep working as a sensor. If I was doing this live, now would be the time I send out on a sample so that everyone can interact with the sample, touch it, play with it, and truly understand this technology. I can't do that, but I'm hoping these images kind of convey how thin, how stretchable, and how transparent these particular pieces of electronics are. So this was technology which we developed, I think around 2014 or 2015. We patented this technology and we thought we have something fantastic in our hands and we'll just wait for industry to come and talk to us, and then we'll get it out of the market, get it out from the lab and push it towards the market. The complication or the beauty of this, however you want to see it, is the fact that this is the platform technology. In the sense, this was something which we could do to any oxide layer. So we could take any oxide layer and render it stretchable or flexible, which meant it opens up a plethora of applications. And so if you want a gas sensor, which is sensitive to a particular gas, it's doable. If you wanted to be sensitive to a particular UV and therefore monitor the UV exposure you have on a day-to-day basis, that's doable as well. If you wanted to be sensitive to certain other things and therefore you wear it on your skin and it's picking up changes within your body, that's something we could do as well. So we didn't quite understand what's the spin we can give on this entire story. And so we kept waiting around, talking to a lot of people and trying to understand what's the best way to get this technology out into market. I spoke to no less than 40 to 50 different industry partners over a period of 2 to 3 years. And I learned a lot, but we didn't really get proper industry connections for a very long time. Partly, it's also due to the fact Australia does not have an electronics industry. We don't actually have the ability to do the electronics manufacturing actually onshore in Australia. So there was a lot of questions around, what do we do with the technology? Do we just license the technology and therefore allow it to be taken overseas? I'm glad we waited it out, because after that, after 2018, there was no stopping Australian startups and them coming to us with their various issues which needed to be sorted out. And therefore, we were able to work with a lot of Australian partners, and now we're trying to work with them to commercialize the work. So sometimes, you get there a little too early, but you have to play your waiting game and wait for the right people to come along, and then you start your journey all over again. This was a very simple example in some sense, but it still takes a lot of time. So this is actually a case where we were making patches. So these are patches which you can stick on your skin. There's no real electronics in this. It's more of a way of using materials together in the correct amount of ratios to get them to be color changing patches. So the idea behind this was, obviously, we have very high incidences of skin cancer in Australia. We are always reminding people to wear enough sunscreen, especially in summer. The sun awareness starts at a very young age, right from where kids are going into childcare. But how do you make sure that people get enough UV in their day to produce vitamin D, but at the same time they don't get that high level of UV that they end up getting some kind of sun damage or skin cancer? And the one more thing added on to this entire thing was, we look around us and we find people are very different. We all have different skin tones. We don't all react to UV the same way as the person next to us does. So one UV sensor is not really going to solve the problem, because it's not a one size fits all model. So there is a little bit of requirement for diversity in technology in this particular space. So we cannot have one technological product which works for everyone in this particular case. We really do need to take into account the diversity of the population. And so we wanted to make sure that we create technology which works for all skin types. So what we created at the end of it were patches which are tailored for particular skin types, where the patch changes color, but it changes color at different rates based on the skin type of the person who's wearing it. And thereby you get the correct amount of color change to warn you that you've had too much UV. And so you need to go back inside and put on more sunscreen. So that's a slightly simpler way of the use of technology, but it wasn't really using any hardcore electronics. It's just a very visible tool to remind you to go in and put on more sunscreen or protect yourself from UV. But it uses a lot of those concepts in terms of it being a wearable, and also it using different materials in it to kind of get the right amount of color change. I'll move on to my next example, and this is a wearable which we are working on with a company called Lepis. This is a relatively recent project. I think we've been working on this now for a little over a year. And what you see over here are what we call smart patches. So with Lepis, the idea behind this was we wanted to have patches which we can place on the skin of people within residential aged care facilities. Now, why residential aged care facilities? It's because in some residential aged care facilities, people need to be monitored quite a lot for their skin temperature changes or for ECG changes or other changes which are happening within their body. So constantly going and probing them and trying to get these readings of them is quite disruptive to their way of life. And it's a lot of work too for the staff who are actually taking care of them. So the question from Lepis to us was, can we create a patch which people can wear on their skin, and you can gather the data of the patch by just using, it's a wireless technology. So use a phone and you get the data of the patch whenever you need it. So the patch which you see over here, you can actually, we developed two kinds of patches for them. One is a skin temperature patch. So just in terms of size comparison, it's just the size of a postage stamp. So it's a tiny patch which sits on your skin, and it's capable of measuring your skin temperature and keep transmitting that data wirelessly onto your mobile phone. The patch which you see here in this particular image is actually a wireless ECG patch. It's fabulous to have this because that means you no longer need wires hanging off you to gather your ECG data. You have this sitting on your skin, and once again, it's wirelessly transmitting the data onto your mobile phone app. In my next slide, I'll just show you a video about how these patches are actually being made. Now, these patches are what I would like to call, they're more of hard-soft integration patches. So they're wearables, but they're not truly entirely soft. There is an integration of hard components, so typical hard silicon components, but encased on a thin, flexible substrate. So sometimes, a completely stretchable or a completely a stretchy and conformal substrate need not be the answer to everyone's solution. Sometimes you just need to think a little bit out of the box and just come up with solutions which work for people. So this is an example of a hard-soft integration where you have silicon components sitting on a flex substrate. So that was a project which we started doing in August last year, and it's phenomenal, the pace at which we were able to actually approach that because of the fact that it's a hard-soft integration process. And those patches are actually now under trial in the UK with the NHS. So they've been actually being trialed with people to actually see what kind of data are we gathering and how usable and how user-friendly are these patches. I'll move on to my final example. In this particular case, it's a nearable. Now, what's a nearable, you might ask? And it's basically technology which is near you, but not on your skin. And so it's not a wearable, but it's more of its technology which is very close to you and therefore still able to get information about you. Now, this was, again, a thing which came as an industry ask. So I think what we learned as a result of the process of engaging with so many industry partners is sometimes it's not about what I as a researcher want. Sometimes it's not about the thing which I foresee is the problem and therefore need to push my research in a particular direction. It's much better if I can actually cater to the market need. So having industry partners who are able to then come and tell us, this is the market need and this is the missing gap over there, and this is a technology which needs to be created. And if we can work with them to achieve those end goals, I think that's much more useful, it's much more fruitful, and I think it's much better for all of us to keep working in that particular direction. So this is a project which is now 3 years old, to be quite precise. So once again, it was something which came to us, Sleeptight, the CEO of Sleeptight came to us in 2018. And again, it's something which was for the aged care market. Now, this was never something I envisioned. If you'd asked me back in 2017, where do you see your technology? I probably would never have said I would see it as a nearable in the aged care sector, but such is life, right? But fabulous kind of story in this particular space, because essentially what Sleeptight came to us was, they said, we know the aged care sector really, really well. And there are multiple issues, but one of the issues which we would really love to solve is the fact that the overnight monitoring of residents in an aged care facility right now, all that happens is a door check. So essentially there's a door check happening every hour on the hour to make sure that the person is in bed. Now, what this does not do is prevent the occurrence, one of the biggest issues in the aged care sector, which is the occurrence of falls. So if a person falls off in that between those two door check times, no one's ever going to find them in that 1 hour period, which means the golden opportunity to actually do something about that fall might be missed. And obviously, you're disrupting a person's sleep multiple times in the night by doing these door checks, which are not really needed for every person that during the course of the night, but sometimes you need to be there at the right place at the right time and prevent the occurrence of falls. So how do we make sure that we can bring technology into the mix and enable the people offering care to these people in the residential aged care facilities to be there at the right place at the right time and enhance their quality of care rather than distributing their time and doing door checks every all through the night. So he said, I know you make micro nano sensors in a micro nano research facility wearing clean room gowns, but can you imagine repurposing your technology? Can you imagine repurposing your technology to make sensors which sit across an entire mattress? So say you have an array of sensors which sit across an entire mattress, and thereby it's kind of a nearable. You have the awareness of a person on bed, and therefore you can pick up if a person is in bed. You can pick up their posture, you can pick up the person's presence, and you can also pick up the person's position and thereby prevent falls from occurring. Now, the funny thing about this kind of a problem is aging or aged care is not an Australian issue. I mean, it's obviously a global issue. People all around the world are aging. And so one of the questions which kind of comes to me all the time when I talk about this particular piece of technology is, why can't you just borrow lessons from other parts of the country and just repurpose that in some sense? I remember presenting this work in Singapore, and I was telling them about making mattress sensors and putting sensors within mattresses and trying to non-invasively monitor residents in an aged care facility. And one of the questions I got asked was, why don't you just put a camera in there and then you know exactly who's there and who's not there, and are they at the risk of falls? Privacy concerns, independence concerns are very different across the world. And I think that's where a lot of the cultural differences kind of come into, in kind of aged care considerations. I come from India, and for us, it's not even an option. We don't even consider the option of sending people into residential aged care facilities. People age in-home. So again, if you're going to launch something like this, then it has to be something which works in an in-home atmosphere. It's not about it working in a residential aged care atmosphere. How do you, give the same kind of peace of mind to the loved ones that they are okay all through the course of the night? The manufacturability was something which we had to consider quite often, because obviously, like I said, we make the sensors in a clean room environment, an extremely contained environment, and we make them at a very tiny scale. Can we actually repurpose this technology to work at a mattress scale and also mass manufacture them in a manufacturing facility, for instance? And user interaction. So, how do you make sure that this does not add more work to the person who's looking after people all through the course of the night, but enables them to just enhance the quality of the care which they can offer? So we worked with them for 3 years, and we were extremely proud to launch this as a product earlier this year in March. It's a product called REMI. So REMI is essentially exactly what we set out to do at the start of the entire project back in 2018. It's a non-invasive monitoring system, which is basically an array of mattress sensors embedded inside the mattress. The person on the bed is not going to feel it. They are there just lying on it, but the person who's looking after them gets a dashboard which allows them to see exactly who's there, who's not there in bed. Are they at the risk of falling out of bed? Have they stepped out of bed and gone away from bed for a really long time, and so do they need to go and be checked on? So just giving them that extra amount of information to allow them to make the right decisions on where they need to be. We also had Sleep Easy on this journey. So Sleep Easy is our manufacturing partner, and they essentially worked with us to convert, what looks like this into what now looks like this. So we've gone from really, really tiny micro nano devices to now having sensors embedded inside a mattress protector. So that's REMI essentially. So if you look at the other side, you're not going to find anything. It's just like a typical cover, but then you have the sensors now manufactured at length, at scale, and now sitting across an entire mattress. You might see the serpentine pattern over there, but that's okay. So that's pretty much what we created. So we managed to transfer our technology and transform it into a mass manufacturable product. There were numerous challenges in this. We really had to almost redesign our entire process, redesign the materials which we're using during the process, because obviously there are other things to consider now. Cost is one of them. The lifetime of the sensors which are being used is the other. And obviously the sensors have to be reliable. The last thing you want is it giving you false data and setting off false alarms. So a lot of things to consider during the process, and manufacturability of it was definitely one of them, which set us along this path. And once we actually made the sensors across a scale on an entire mattress, we subjected it to what is called a rollator testing. So a rollator is basically something which applies equal pressure on the mattress. This is how mattresses are tested, by the way, in bedding facilities. But we put through our sensor technology product through the exact same kind of testing. So run a rollator on it multiple times to make sure that it's able to withstand multiple rollator cycles, and therefore, have a lifetime which you can promise people that this particular technology will last out there for them, and not just go away the first night they've actually lying down on it. It no longer works reliably. So we created REMI, and then we realized it actually doesn't stop at aged care. So thinking about it, having the ability to get information while people are asleep, it allows us to do a lot more than just offer enhanced protection within aged care facilities. You can do sleep science studies with it. So this was we're now working with Flinders University to try and undo sleep studies. So sleep diagnosis evaluation is also something which we can do with this particular tool. And doesn't really stop at aged care, right? I mean, whether it's aged care, aging inside a residential aged care facility, or it's aging in home, we can practically see this kind of technology, go across all those sectors, or any other sector, be it defense, boarding schools, prisons, or even for kids, for SIDS prevention. So if you can have REMI sitting on a cot, for instance, this is something which you can use towards SIDS prevention at the early stages of an infant's life. Fascinating. And like I said, this is never something which I would have envisioned. Like if you'd asked me in 2016, where do you see your technology out in the market? I probably wouldn't have said in the form of a mattress sensor for aged care, but that's just where life takes you sometime. And it's a fascinating and truly amazing journey to have come this way to create REMI. I'm going to pretty much summarize my talk on that particular line. And this is more of a thing to show you that, we do different things all through in our labs. And sometimes it's about not just doing a particular job on a particular day, but it's working with a team, staying motivated, to cross all those challenges which we work through all the time. We are blessed to have a very diverse team working with us. I'll show you a photo of them in the next slide. But that diversity in the team, I think, lends to a lot of our creativity. It lends to a lot of our innovative ideas which we have within the team. And that allows us to work together and come up with new solutions for a lot of our problems which are there. We collaborate quite widely, and industry partnerships are some of those examples which I showed you, but we also work quite a lot with design partners. So to try and understand and envision our product in the market and truly understand the user experience for our end product is something which is very important to us. So having that cross-disciplinary collaborations where we work with design partners is something which I think I've learned a lot from that particular process. And that's definitely something I would recommend to anyone who's trying to get an electronic product out into the market. That's the fabulous team. None of this will obviously exist without them, their hard work all through. It's a very diverse team, an international team predominantly. A lot of them working together, staying motivated and staying passionate and committed to the research is what allowed us to achieve a lot of the goals which I presented to you today. And obviously the funding partners who have supported us in different shapes and forms right from the beginning, be it the fundamental research or be it the research which we do with industry. Thank you.
Thank you very much for that talk. I'll start with the questions. I'll execute my privilege of being able to ask the first question. You've discussed nearable and wearable sensors tonight. Obviously, the next stage beyond that is embedded sensors. Is that something that you've looked at or you've got any plans of developing at this stage?
So embedded as in, you mean embedded inside the body?
Yes.
I don't, but there are lots of groups who are working on that. Well, obviously, there's biocompatibility is one of the key things in that, and biosolvability and it, dissolving in the body and things like that. So people do a lot of work on that. We haven't done embedded sensors, but one of the early work which we are working on is where we are truly trying to create electronic skin. So it's kind of skin which kind of mimics the properties of real skin. I actually, coincidentally, I think I have that's the future. That's what we're hoping to have one day, have skin which we can stretch on top of prosthetics, and it behaves just like real skin and therefore lends, much better lifelike experience to prosthetics, because this has the ability to have electronics embedded in it and talk and work with the brain and behave like real skin. So this is something which we're working on, but not an embedded.
Excellent. There was a question, I think, that pertained to the UV sensors. How long do the sensor devices last in sunlight?
So we've tailored them to work in such a way that for your particular skin type, if that particular skin type under a particular UV range is the kind of person you need it to last that long. So it's more of trying to tailoring it back to the UV exposure on that particular day, your skin type, and also if you applied sunscreen on top of it, then it also has the ability to mimic the way sunscreen wears off on skin and therefore wears off on the sensor as well. So it'll mimic exactly what your skin is undergoing on that particular day due to the UV exposure or due to your particular skin type.
There was a question. For measuring ECG, the 12 lead electrodes have to be positioned in Einthoven's triangle pattern on the left shoulder, right shoulder, legs, and on the chest for measuring conductivity across the body from various angles, inferior, lateral, anterior, and septal views. How is this achieved in a device the size of a postage stamp?
That's something which so we've created this and it works well. There's a lot of research which is still doing in that particular space and trying to understand what's the most optimum design, what's the optimum placement for this particular patch, and how accurate the signal is compared to what you might get out of a 12 lead ECG. It's highly reliable, it's highly accurate, but to how much data do we extract from this as opposed to what we extract from a 12 lead ECG? That is something which we're still waiting to see. It wouldn't be the same as that. And look, this is not something which we're looking as a replacement for a 12 lead ECG, but what we are hoping this would do is pick up those initial changes or those alarming changes, which then allows you to tell, okay, I need to now go and get a really proper ECG done with the 12 lead machine, which will allow me to understand better what's going on. So it's more to pick up abnormalities rather than getting the full ECG experience, if that makes sense.
There is another question. Is there scope for using this technology in monitoring experimental animals?
I would say yes.
So would I. How are the devices powered?
They can be powered in a few different ways. So battery is obviously one of the things which we can use to power them. So some of them are powered using batteries, especially the ones which work off a Bluetooth connection. Some of them are NFC powered. So it's a bit similar to, the chips which are sitting within your credit card. So just as how it only works whenever you interact it with a reader, it's a very similar kind of technology. So where you have NFC and it's only working whenever it's communicating with that particular reader. This battery considerations are definitely something, and that's which I don't personally work on, but a lot of people are trying to overcome those issues on how do you make batteries smaller, thinner, less power hungry, and more energy efficient, and still have it within a wearable. So that's a big field of research. But for the ones which we use, these are what we go with.
Actually, presumably you can use inductive, but I've also heard of technologies where people are working on clothes that generate electricity as you move. So
that was my previous life. So I worked for 3 years on piezoelectric materials from 2008 to 2010. That was pretty much my life, making piezoelectric materials and trying to generate electricity from my aim was to generate enough electricity from blood pressure so they can power pacemakers. That was my golden aim back then.
Well, there's an actual marriage there should they succeed. There's another question which I believe you've answered, but I'll ask it anyway in case I've misrecalled. If a stress is applied by 20% and the function ceases, then the stress is removed, will the function be restored? And I think they were talking about your tectonic, microtectonic technology there.
Yep. So there is up to a particular percentage that you can completely recover, but so up to 20-25%, we can recover and go back to its original state. But beyond, say you push it beyond 30% or so, then you kind of kill the circuit and it's irrecoverable beyond that particular point. But up to 20-25%, it might not work as well at 25%, but once you go back to 0%, it goes back to being its original condition.
I've seen circuits being applied to cloth. I take it there's no limit on what substrates you can apply this technology to?
With the right manufacturing partners and with the right manufacturing tools, you can. Like for instance, like with REMI and with the Neurable I was talking about, that was a big journey for us to go from having it on a thin contact lens type material to actually integrating it on fabric. So now that we have the ability to integrate it on fabric, then yes, I can now comfortably tell you that I'm comfortable that I can integrate this particular technology on fabric. So it depends on what you're trying to integrate on. There is a journey to go through there in terms of manufacturability, but you can get there.
I'll give people a few moments to write any last questions and just let everyone know that the next ANZAAS talk will be on the 20th of October with Professor Cam Simmons, World Mosquito Program, a breakthrough in combating dengue fever that might also work for other parasitic diseases. There was certainly a lot of congratulations. So on behalf of the audience, I would like to thank you very much for your presentation tonight. It was very interesting and informative.
Thank you.
On behalf of everyone, I'll give you a round of thank you very much indeed for your presentation tonight.
Thank you so much.
I call tonight's talk to a close. Thank you very much, everyone, for coming.